Okay, let's do an example of an electromagnetic wave. In North America, many cell phones operate at a frequency of 1900 megahertz. First, about units. M stands for mega, which is the same thing as million. So a mega is times 10 to the positive 6. Many cell phones operate at a frequency of 1900 megahertz. What wavelength is associated with that frequency? Well, we know V equals F lambda, our wave equation. The speed of a wave is the frequency times the wavelength. An electromagnetic wave, which is what cell phones and other electrical equipment operate on, an EM wave has a speed equal to C. So our wavelength lambda is V divided by F, or C divided by F. C is the wave speed of any electromagnetic wave in air, which is 3 times 10 to the 8 meters per second, divided by the frequency of 1900 megahertz, so 1900 times 10 to the 6 hertz, gives a wavelength of 0.158 meters, or 15.8 centimeters. So that's the operating frequency of a cell phone. So my next question in this example is, how big is your cell phone? Right? That's a good question. So here is my cell phone. I'm going to hold a ruler up to it. My cell phone, it's hard to be exactly accurate. I've got a case on it. It's hard to see it exactly. It's like between 15.5 and 16 centimeters. So my cell phone is about 16 centimeters. Is there a connection between the two? Well, the size of my cell phone is pretty close to the length of the electronic EM wave. So if you think about how your cell phone works, your cell phone operates by getting an electromagnetic signal, by catching this wave. The way it catches the wave is there's an antenna inside your cell phone, and the antenna is more or less the length of the cell phone. So if your antenna is going to receive this signal, the size of the cell phone has to be comparable to the wavelength of the signal. So is there a connection between the two? Yes. Cell phone size is comparable to the wavelength. And that's so that the antenna inside can receive the EM wave, or the phone signal. Okay, so that's one example. Next, we'll just talk a little tiny bit more about light waves. We'll talk about light waves in a medium, not just in air or in a vacuum. So let's think about the speed of other waves we've discussed. We said that the speed of a wave on a string depends on a string through the tension and the size and the mass. The speed of sound depends on the medium. So in a gas, it depends on the temperature. What about light? So to help us think about light, if you're on the beach and you're running through the beach and all of a sudden you run into the water, what happens? Well, the first thing that happens is you slow down. So we know that the speed changes when you change a medium, and we need to write down how that change in speed depends on the medium itself. For light, we use something called the refractive index. So when light enters a transparent medium, so something it can go through, it slows down because there's a resistance to the wave going through, just like you trying to run through water. So there is a resistance. We write the speed of the wave in the medium. So we call that v. So that's the speed in the medium. This could be something like glass or water, just some medium that water can go through. It's equal to the speed of light in a vacuum, and that's our 3 times 10 to the 8 meters per second, divided by n, which is called the refractive index or the index of refraction. You may be used to studying n using Snell's law in a high school physics course, and that is this same n. N gives us a measure of how much the light wave slows down in the medium. So we have some indices of refraction over here for different media. In a vacuum, it's exactly 1. In air, it's almost 1. So a vacuum and air are not that different. In water, it's about 1.33, glass 1.5, diamond 2.42. So it varies in different substances, but it's always bigger than or equal to 1, always. So there's no substance that light will speed up in. So that tells us about the speed. What about the frequency and the wavelength? Let's have a look at those guys. So what happens to frequency and wavelength? Well, frequency, and I want you to hit pause here and think for yourself. Do you know what this answer is before you come back and look at it? Once you've decided the answer, come on back and we'll think about it. So for frequency, we have to think what makes the frequency, and this might even be easier to understand if you think about sound. The frequency of the sound waves that we described in the previous slides depended on how fast the diaphragm of the speaker was pulsing in and out. It was the motion of the diaphragm that caused the sound wave. If we take that same speaker and we put it under water, let's assume it's waterproof, it'll still move back and forth with the same frequency. The frequency of that wave won't change. So F is going to be constant. And the reason that F is constant is because the frequency depends on the source. Hang on, I gotta close the door. These are the hazards of teaching from home. Sometimes you guys are going to end up hearing my husband talk to the dog. And it is a lovely conversation to overhear, however. So the frequency is constant because the frequency depends on the source. So now we've settled what happens to the frequency. I think that more or less tells us that if V changes, lambda will also change because we know V equals F times lambda. So let's write this bit down first about our frequency being a constant. So F in a material equals F in a vacuum. So the frequency is a constant. Well, now let's add in the fact that V equals F times lambda, which tells us that F is V over lambda, but V is the speed of the wave. So in a material, we've got the V in the material divided by the wavelength in the material. We've already established that we think the wavelength is going to change. If F is constant and V changes, something has to change, and that thing is going to be the wavelength. Is equal to the frequency in a vacuum. The speed in a vacuum, V of a vacuum, that's equal to C. Divided by wavelength in the vacuum. So now what we'll do is, let's see, what can we say about the V of the material? V of the material, to use this relationship up here, is C divided by N, where N is the index of refraction of the material. So let's fill in those two little bits. C over N over lambda of the material equals C over lambda for the vacuum. Got a C in both those guys, so they cancel. Then we can solve for the lambda of the material. So we'll bring that up here, we'll bring this up here. Lambda in the material, so the wavelength of the light in the glass or the water, whatever material we have, is the wavelength in the vacuum divided by the index of refraction. So there's a couple of relationships we have now to tell us about how the speed changes. So the speed changes, the frequency stays the same, and the wavelength changes. Some people find it useful to compare this to a marching band in a parade. I don't know, like the Santa Claus parade or ever, if you want to think about. So if the marching band is playing their music, playing their song, they have to march in step with the music. They have to match the frequency. But if the parade slows down because kids stop to say hi to Santa and the marching band needs to keep the beat, then they have to take smaller steps. Otherwise, they'll all pile up on top of each other. So some people find that a useful analogy. Okay, one more example. So in our example, purple light, we'll think about, we've got a picture here, has a frequency of 7.5 times 10 to the 14 hertz. It's incident on a 1 millimeter thick glass slide. So here's our glass slide. It's got a thickness of 1 millimeter. And now we're going to ask some questions. The first question, what is the speed of the light outside and inside of the slide? Okay, outside is really pretty simple. Outside, the index of refraction of air is close to 1.0003. So the speed in the air is about equal to c 3 times 10 to the 8 meters per second. What is the speed of the light wave inside the glass? So inside glass, n of glass is equal to 1.5. It can be different for these different types of glass. I'm going to say that this one has n equals 1.5. So the speed of the light wave in glass, we'll remember from the last slide, the speed is c divided by the index of refraction. So 3 times 10 to the 8 meters per second divided by 1.5 gives us a speed of that light wave in the glass of 2 times 10 to the 8 meters per second. And then next we'll ask how many wavelengths are inside the slide. So if we want to figure out the number of wavelengths, let's recognize that the number of wavelengths inside this glass slide is going to be however thick the glass is divided by the wavelength inside the glass. So for example, if this thickness corresponded to 1 wavelength, there'd be 1 wavelength inside. If it were twice as big as a wavelength, there'd be 2 wavelengths inside. So if we can see how many wavelengths, if we can see what the ratio is between the thickness and the wavelength, that's going to give us the number of wavelengths. So we know the speed in glass, we want the wavelength in glass. Let's see how we're going to find that. There's 2 ways we can do it. So we can go with the equation we found on the previous slide. Lambda in the glass is going to be lambda in the vacuum divided by n. So 2 ways, they're really the same way. Lambda in the glass is lambda in the vacuum, or in air, divided by n. Lambda in air, we'd have to figure out from up here. We know that V equals F lambda. So lambda would be c divided by the frequency. You would divide that by n. So that's one way you could do it, absolutely valid. And you could even find this lambda air first if you wanted to. Or we can say that lambda in the glass is V of the glass divided by n. V of the glass we already know. So 2 times 10 to the 8 meters per second divided by 1.5 equals, oh my goodness, I goofed. Lambda is v divided by frequency. So it's the speed over the frequency gives us the wavelength. The frequency was 7.5 times 10 to the 14 hertz. And that works out to be 2.67 times 10 to the minus 7 meters. So that's the length of a single wavelength. So from here to here. So there's one wavelength lambda in the glass, of course. If you wanted to see that these two equations were exactly the same thing, you could go a little further with this equation. So that's C over F times N. C over N over F equals V in the glass over F. So really they're the same way. Okay, so we know how big one wavelength is, we know how big the slide is, so let's see how many of these wavelengths fit in this slide. So we have 1 millimeter divided by the size of one wavelength, and that gives us 3,750 wavelengths. That is lots. So sometimes with these problems you could just draw it out and count. I wouldn't recommend that for this problem because you would have a lot of counting to do.